So we're going to start the 9.4. We're going to do 9.4 today. So last time we talked about integral test. We got a series, and we want to know whether this series converges or not. In other words, we want to know whether the infinite sum of the numbers of a sequence give a finite number or not. And that's what it means by convergence or converge. We have talked about some special cases of a series in 9.2, like the telescoping series, the geometric series, and those are the bases for us to use before we can use other strategies like the comparison test today. But we also covered in 9.3 the integral test. That's a method that to determine the series converges or diverges. So you just change the problem with summation of discrete terms into integration. Okay. So you integrate the function from 1 to infinity and see if it gives you a finite number or not. Now the function you choose is just the generalization or extension of the series. We just change n to x in the series general form and then integrate it. Okay, so that's the first method we talk about in general. All right, and then we're going to talk about another method, the comparison of series, to determine a series convergent or divergent. Okay, so you should have some ideas in mind, some spatial series that we will use it as the basis, and then the methods. Okay, we just talk about the one method, the integral test in 9.3. We're going to discuss the comparison of series today. That's another method. And there are two versions of this comparison methods. The first version of the first method is called the direct comparison test. So then you need two series, and one is A and one is B, and both the series are positive or zero sometimes. They could have some zero terms, and the one series is dominated by another series. An is greater than equal to 0 and less than equal to bn or equal to bn. So an is dominated by bn. So bn is more than an, basically, if you sum up. So that means we can use these two tests to make a comparison. If you know the series bn converges, then the series an must converge. Okay, because an is greater than bn is greater than an. If the greater series sum up to a finite number, then the smaller series also sum up to a finite number because they are all positive, okay, or zero. And then conversely, if you know an diverges, the smallest series diverges. It sums up to, blows up, the sums blows up. Then the larger series being also diverged because it is even larger and they're both positive. Okay, that's important. So you take the direct comparison of these two series and see whether they are convergent, divergent based on the other series. Okay, let's do some more simple examples by using this direct comparison test. Let's see whether the series of 1 over 2 plus 3 to the n diverges or converges. Okay, we can use the direct comparison test. So we need to find another series to compare. Okay, so we only have one series, 1 over 2 plus 3 to the n in this problem. So we need to find the reference series to compare. So let's just name an to be 1 over 2 plus 3 to the n, and bn to be 1 over 3 to the n. So you just take off the 2 in the denominator. Then obviously an is less than bn. Why? Because you got more numbers, a larger number in the denominator in an. Okay, so an is less than bn. And we know bn is just a geometric series. If you write it as 1 over 3 to the n, you can rewrite 1 over 3 to the n as 1 over 3, the whole thing to the n. So that's a geometric series with r equal to 1/3. Remember, the ratio r is the ratio of the two consecutive terms. All right, in this series, you just multiply 1/3 by itself more and more times. So the ratio of two consecutive terms is just 1/3. And that is less than 1. So it says, if you remember, if a geometric series has a ratio r less than 1, then the series converges. So that means Bn converges, and we know Bn is greater than An. So An has to be convergent because obviously two series are positive. Okay. So by the theorem, series An also converges. Any questions? Okay, we're not dealing with the negative series here. All of them have to be positive. All right, so that's the first example. And let's do another one. Okay, this time we have the series of 1 over 2 plus squared n. This time we're going to choose 1 over 2 plus squared n as bn in the problem. Okay, we choose bn as and we choose another series for reference, which is 1 over 3 squared n. We call it an. So then we can easily get the argument that an is actually less than or equal to bn. Why? As n greater than or equal to 1, that's obviously the case. Then we have square root of n is greater than or equal to 1. Obviously, take the square root. It has to be greater than 1. And then multiply 2 on both sides of this inequality, you get 2 squared n is greater than or equal to 2. And then you add another squared n on both sides of this inequality, so you get a 3 squared n on the left and a 2 plus squared n on the right. And if you take the reciprocal on both sides of this inequality, then the inequality reverses. So we get 1 over 3 squared n less than or equal to 1 over 2 plus squared n. And 3 squared n is just a, and then 1 over 2 plus squared n is just bn. So n is less than or equal to bn. Now, then we look at the reference a and see whether it's convergent or divergent. So n is just 1 over 3 squared n, and you can take out the 1/3 from the sum. So you get the 1 over squared n inside the sum, and then that can be rewritten as 1 over n to the half. And the series of 1 over n to the half is a p series with p equal to half. And remember we talked about p series last time. 1 over n to the p. When p is greater than 1, the p series converges. When p is less than or equal to 1, the series diverges. Now, in this problem, p equal to half, so it's less than 1, so this series diverges. That means the sum of all of those 1 over n to the half blows up. If you multiply 1/3 on it, it still blows up, right? It's infinity, you multiply 1/3 is still infinity, all right? So that means n diverges. Now by the comparison test or direct comparison test, because an is less than or equal to bn, so if an diverges, then bn has to diverge. So by the theorem, we got the series bn, which is 1 over plus squared in a problem, also diverges. Oh, I wrote the two V's in here. Okay, that's a typo. So sometimes you have to find out the good series to compare to reference series to find the good reference series to compare. All right. So that's example. Any questions for the problem? We got a little more people today. 14. More people will join later. So that's the first version of this method. We have another version of this comparison test. It's called a limit comparison test. So this time, again, we're talking about two positive series A and B n, and we don't require one series to dominate the other. Instead, we require the limit of the ratio of the two series to be a number greater than 0. It cannot be equal to 0. It has to be greater than 0. All right, that's the important thing in this limit comparison test. So you take the limit, and that's why it's called limit comparison test. So what it says basically is these two series are actually comparable. They are on the same order to approach 0, A n and B n. Remember. So then the conclusion is the two series A and B n are either both converge or both. That was not OT. I'm sorry. So this is a different comparison test. You take the limit of the ratio of the terms in the series, and then you see if they are given a positive number, and then you can determine, either both converge or both converge. All right. Okay, so let's talk about a series 1 over am plus b. That's called the general harmonic series, if you remember. The harmonic series is 1 over n. And if you put more terms in the denominator, am plus b, that's called the general harmonic series. And it's a and b are constants and the positive. Okay. So what is changed is just n as usual, right? So we want to know whether this series converges or diverges. So again, we're going to use the limit comparison test. In this case, we're going to let a n equal 1 over n and b n equals 1 over a n plus b. So we're going to compare 1 over a n plus b in the problem with the series of 1 over n, as we know. That one is the harmonic series, and it is divergent. Okay. So what we do, just take the limit of the ratio of a n over b n. Put that in, we get 1 over n over 1 over a n plus b. If we put a n and b in this limit, and then you just flip it when you divide the fraction. So we got 1 over n times n plus b over 1. So that becomes the limit of n plus b over n and approaching infinity. And just like we always do, split the fraction into two terms using the same denominator. So we get a n over n plus b over n. N is just a, if you cancel n, and b over n has the limit 0 because when n approaches infinity, the denominator blows up. So we get a plus 0, so that's equal to a, which is positive. Okay, we have assumed a and b are both positive in the problem. So use the limit comparison test. You will know the an series an is 1 over n. That's the harmonic series, and it diverges. So by the theorem or the limit comparison test, the series of bn, which is 1 over n plus b, also diverges. They have the same order, on convergence or divergence. Any questions for this problem? Oh, we got 14 people. We're gonna have a relatively short section today, so we don't have to rush. Let's just do some more examples by using the limit comparison test. In this example, we want to find whether the series square root of n over n squared plus 1 is convergent or divergent. So we're going to use the limit comparison test. So again, we let that be n equals square root of n over n squared plus 1. That's the problem we have. And we just drop 1 in the denominator and I get another series, and we call it an. So n is just square root of n squared. Okay. Actually, you can name either one an or bn. It really doesn't matter. Okay. Because at the end, they will have the same order of convergence. Okay. So I just follow this procedure of the limit comparison test. Take the ratio of n over bn and take the limit with n approaching infinity. So plugging in this limit, we got the square root n over n squared over square root n over n squared plus 1. Again, flip the denominator, we got square root n over n squared times n squared plus 1 over square root n. And then the square root n cancels on the top and at the bottom. So what is left is just n squared plus 1 over n squared. Again, you split this fraction into 2 from the denominator, from the numerator. So we get n squared over n squared plus 1 over n squared. And the first term is just 1, so we got 1 plus 1 over n squared, and then the limit of 1 over n squared as n infinity is 0, as we know. So we got 1 plus 0 equals 1. So that's positive again. So these two series have the same order of convergence. And then we need to know, whether the reference series n, which is the choose divergence or convergence. So n is greater than or n squared, and we write square root n as n to the 1/2, and then and a half n to the half over n squared is 1 over n to the 3/2 if you subtract half from 2 in the denominator. Okay, remember? So this is a p series with p equal to 3/2, and that is greater than 1, and we know a p series 1 over n to the p1 p is greater than 1, and it converges. So we know this series converges, the reference series converges. So by the theorem, or by the limited comparison test, the series Bn, which is the problem we have in here, also converges. All right. Any questions? No question. Then let's see. We got one more problem. This time we got a little more complicated. We have a problem of the series of n times 2 to the n over 4 in cube plus 1. Okay, so we're going to use the limit comparison test to see whether it converges or diverges. So again, we're going to drop 1 in the denominator to make the reference series to be n times 2 to the n over 4 in cube, and we call it a, and we call the original series in the problem B. So you can see it is always the thumb or rule that you drop something in the original problem and use that as the reference series. Okay, so when you drop something in the original series, the problem will be most likely more simpler, and that you can determine, whether this reference series converges or diverges. Okay, so let's try to use the limit comparison test to see whether these two series converge or diverge. Okay, so take the limit of n over bn with n approach infinity. So we got n times 2 then over 4 and cube on the top, and then n times 2 then over 4 and cube plus 1. So again, flip the denominator, we got the 4 and cube plus 1 over n to the 2 to the n. Then we can cancel a lot of things in here. We can cancel n and the 2 to the n on the top and at the bottom. And then we are left with 4 and cube plus 1 over 4 and cube, just like before. Okay, so always like the same kind of things. So we just break up the fraction into 2 by the numerator. So we got 4 and cube over 4 and cube plus 1 over 4 and cube, and the first term is just 1, and the limit of 1 over 4 and cube is just 0 as n approaches infinity. So we got 1 plus 0, which is 1, and that's positive. Okay, it's greater than 0. And then we need to know whether the reference series an, which is n times 2 to the n over 4 and cube, converges or diverges. All right, this seems pretty difficult, but actually, if you start, from the nth term test, and you are gonna find that this series actually diverges. If you still remember what the nth term test is, it says for a series to be convergent, for the infinite sum of the numbers to be finite, then the numbers on the tail, okay, have to converge to 0. They need to have the limit 0 as n approaches infinity. So an needs to have a limit 0 for the series to converge. That's called the nth term test. The limit of n is not 0, then you can automatically tell that the series, okay, diverges. Okay, so basically we need to find the limit of an as n approaches infinity. So that's the nth term test. But again, this is still not quite an easy job. Okay, we got a exponential on the top and the power at the bottom. So we're going to change this series problem to a function problem. So we're going to define f of x equal to x times 2 to the x over 4x cubed. So what do you do? Just change x n to x everywhere in an and call it f. So you can cancel x on top and the bottom to get 2 over x over 4x squared. And obviously f of n equals a n because that's how f is defined. And why do you want to do that? Then we can find the limit of f, and the limit of the an, the sequence n, must have the same limit of the function f. And because now f is continuous and differentiable, then we can use the L'Hopital's rule to find the limit. Okay, as x or n approaches infinity, then 2 to x, also approaches infinity. You get the infinite number of 2's multiplied by each other, so that blows up. Also, the bottom of 4x squared blows up because the x approaches infinity, so you squared the approaches infinity also. So we can evaluate the limit of f as x approaches infinity instead of n. I'm sorry, that's a typo in here. It should be the limit of f as x approaches infinity. It's just that 2 to the x or 4x squared. If we use the L'Hopital's rule, if you remember that, the L'Hopital's rule applies to indeterminate format or indeterminate form. Namely, if you have two large numbers divided by each other, okay, or two extremely small numbers to divide by each other, and you want to see, which one goes faster, okay? So in this problem, the numerator and the denominator both approaches infinity, but you want to know which one goes faster. So for that kind of situation, you can use the L'Hopital's rule to take the derivative of the top and the bottom separately, and then try to evaluate the limit. Okay, so when you take the limit of 2 to the x, you get 2 to the x times n and 2 if you check the formulas for derivatives. And then obviously you take the derivative of 4x squared equal to 8x using the rule, right? Everybody knows that. And then, if you try to evaluate the limit as x approaches infinity, then you still get the infinity over infinity, because 2 to the x again approaches infinity, and in the denominator you get x. So it's another indeterminate form that we can use the L'Hopital's rule again. So what you do, just take the derivative on the top and the derivative at the bottom, and evaluate the limit. Okay, so on the top we already got n and 2 that we can take out. And then if you take a derivative of 2 to the x, you get 2 to the x times n and 2. So that's where you got 2 n and 2 on the top. And at the bottom, the derivative of 8x is just 8. So now you can value the limit easily, because you just get the constant at the bottom, but you do have 2 to the x on top. So the numerator blows up and denominator is extended. So the result will be blowing up. So this limit approaches infinity. So the function f approaches infinity as x approaches infinity. So that also tells that sequence an approaches infinity. So it's not 0. Okay. So the limit of an is not 0, and that automatically tells that the series will converge. Remember, if the sequence n has a non-zero limit, then the series of an diverges. Okay, that's the nth term test. So now we know n diverges, then because an and bn have the same order of convergence, the limit of the ratio of the terms is greater than 0, then A and B have the same properties of convergence and divergence. And that means also B and also divergence.